I'm going to show you a tension member design example. So for a typical design problem, usually the maximum applied load PU is given based on the most critical load combination. And then we're going to find the lattice member with VPN smaller than PU. We want to choose a member based on the simple calculations and the reasonable engineering judgment. Once we pick the member, we want to check the member for all the limit states, including yielding, fracture, and block shear. And don't forget to check all the members connecting together, right? So not just the member you are looking at, and like the tension members in the example is connected with a gusset plate. So you not only check the member you select, but also check the tension strength for the gusset plate as well. Recall the design strength VPN is the lesser of the yielding state VFYAG or fracture VFUAE. So we want to find a member with VPN either VFYAG must be greater than PU, right? Or this one, VUFUAE, must be greater than PU, right? So from there, we know that the gross area required equals the larger of AG, larger of PU divided by phi Fy, right? Phi. So this phi equals 0.9, right? Or PU divided by phi Fu, okay? And this phi equals 0.75, and plus the estimated whole areas, right? Because from this equation, we get AE must be greater than PU divided by phi Fu, and AE is can be approximately equal to AG minus the whole area, right? The whole areas, right? So greater than PU, Fu, Fu. So that's how we come across this expression. So of course we have to account for U, right? So AE equals U times AN, right? All right. And in addition, to prevent undesirable lateral diffractions or vibrations in members designed based on tension, the slenderness ratio is suggested to be smaller or equal to 300. So that is required by AISC section D1, okay? And L is the length of the tension member, or length of the tension member. Or the spacing between the spacers. Okay, so and note that different code gives a different suggestion. So like Ashto specify a maximum slenderness ratio of 200. 200. For the main tension members and 240 for secondary tension members. Okay. Okay, so let's look at the problem given. So given a tension diagonal member of a roof truss is subject to axial force of 60 kips. And dead load and 6 kips live load. And the member is 12 feet long. The connection at each end of the member will use a single gauge line of 7/8 inch diameter bolt with standard holes. And the preferable limit on slenderness is 240. So in this example, Ashto specifications for secondary tension members criteria is adopted. Based on this information given, we are to find the lightest single angle member or find the lightest double angle member having legs separated back to back, and use the A572 grade 50 steel. Right, so that's maybe the look the look of the tension, the double the angles, the angle tension members. So we can either choose a single member, a single angle member to make this connection, right? So like for example, see, this is the gusset plate, and we bolt a single angle member on the gusset plate. Or choose a back-to-back double angle, right? So double angle member, back-to-back connected to the gusset plate. And the preferable gauge distance is specified or suggested in the code. the new code is page 1. The new code is page 152, table 178. Right, so the gauge, the walkable gauge distance is specified in the table 178. So, right. Then, first of all, we want to check the possible or the governing load combinations, right? So obviously, the first load combination, the dead load combination, controls the design. So the VPU we're going to use to design member is 84 kips. All right. So like what we have done before, so first of all, we have to check the yielding limit states, right? Yielding limit states is equals to 0.9 times Fy. So for the A572 steel, Fy is 50 ksi times the gross section area. And then VPN based on fracture is 0.75 times Fu, which is 65 ksi times, sorry, this should be AE. So this should be AE. Okay. So we have to size the tension member first, right? So recall that the required, so based on yielding, the required AG equals PU, because this number has to be greater than PU, right? Has to be greater than PU. So required AG would be PU divided by VFY, and plug PU, the controlling PU, into the equation. So PU is, we just determined, which is 84 kips, divided by phi for yielding is 0.9. Oh, this should be, so for yielding, we should use Fy. So that's Fy. Okay, so 0.9 times 50 KSI, okay, equals 1.87 square inches. Okay, so that's based on yielding. And then let's look at the required AG for fracture. So from there, we know that the required AE is PU divided by phi FU, right? So PU still 84 kips divided by, so this phi is 0.75 times 65 KSI equals 1.72 square inches. Okay, so remember that is the required AE. Okay, so this is the required AE, not AG yet. So we need AG to size the member. So the required AG, so recall that AE equals UAN, right? So AN equals AG minus the whole areas. Whole areas. So AG AG, the required AG for fracture. Okay, so let's say the fracture equals AE divided by U plus whole areas. We don't know U yet, right? And whole area, the whole area we don't know yet. So determine how many bolts we want to use. So here we just assume, make an assumption, right? And check later. So assume U equals 0.85. So AG equals AE. Required AE we calculated as 1.72 square inches divided by 0.85 plus whole areas. So this part alone equals 2.03 square inches plus whole areas. So as we can see, this part alone greater than the required gross area based on yielding, right? So it must be greater than 1.87 square. Don't forget the slenderness requirement, right? So R is in the problem statement said L divided by R man. R man is the minimum radius of gyration. Must be let's see. Must be smaller, right? Must be smaller than smaller than 240. Okay. So once we select the member shape, we should be able to determine the value of R min. So from there, L, we take L as the total length. See, there's no spacing in between. There are no spacers in between. So R min must be greater than, so the length of the member is 12 feet long, so convert it to inches. 12 feet times 12 and divided by 240 equals 0.6 inches. Okay, so that's don't forget to check that slenderness requirement. Okay, so we determine the after determining the cross-sectional area, so we can size the member. So there are several different let's see, thickness. So say if there are 16 thickness members, okay, and and also there are 3/8 thickness members and 7/16 thickness members. So the unit is in inches. Okay, and then the deduction for one hole, right? So from before, we know that there's only one row of the bolt, so only one hole gonna be deducted from the gross sectional area. So the thickness, the deduction for one row is for 5/16 thickness. So for T equals 5/16 inches. The deduction for one hole gonna be the deduction equals the hole diameter. The bolt diameter is 1/8 inch plus 1/8 inch and times the thickness 5/16 inches equals 0.313 square inches. Right? So the required AG would be equal to the required AN. Okay, so required AN would be, let's go back. All right, so if we go back to the previous analysis, say the cross-sectional area based on fracture would be greater than the required area based on yielding, right? So we want to calculate AG based on fracture. So the required AG, so going back, equals to 2.03 plus the whole areas. So is 2.3 square inches plus the estimated whole area, which is this one, right? We just calculated, equal to 0.313 square inches. And we get a number of 2.34 square inches. Okay. And then check our man. And then check our man. And our man is the smaller of lesser of Rx and Ry, right? Okay, so deduction for one hole for 5/16 thickness single angle is 0.131. So the unit is the squared inches. Okay, squared inches. And the required we just calculated as 2.34. Okay. And similar, we can also calculate the deduction for 3/8 inch diameters. So for T equals 3/8 inches, so the one hole deduction is also equals to the whole diameter, which is 1 inch, times the thickness, so 3/8 inches, which equal to 0.375 square inches. Okay, and the required AG is also equals 2.03 square inches, and plus we just calculated 375 square inches equals almost equal to 2.40 square inches, right? So we fill out okay, so similarly we can also fill out the numbers for 7/16 thickness single angles, which is 0.43A and 2.47. Okay, so those are based on the required gross area. We can select some shapes, the shapes from the menu, and then we know that there are several shapes qualified. Say, for example, there is a single angle 3/1/2 by 3/1/2 by 3/8, and this one has no gross sectional area of 2.50, and the radius, the minimum radius is which is lesser of Rx and Ry, is 0.683. So which is greater than 0.6, right? So greater than 0.6. So we are fine for the slenderness requirement. And we can also select member L4 by 3 by 3/8 inch, and the gross sectional area is 2.49. Rman is 0.636. Okay, and L3 by 3 by 7/16. So AG equals 2.383. That's it. This one is a little bit smaller than the required, a little bit smaller, and Rman is also a little bit smaller. Okay, so I think the first one would be preferable, so we can select that one and then check the design adequacy later. All right. So that's the example of select a single angle member, and we can also try the double angle member, right? So similarly, we can try the standard word double member with a standard word thickness of 1/4 inch. So the deduction for one hole, as you can see, so saying that draw it here. So for the double angle, okay, so the cross sectional area is the total of the two angles. So there are two holes need to be deducted from the cross section area. So the deduction for one hole is equal to two bolt diameter plus 1/8 and times 1/4 thickness. And is equal to 0.5 square inches. So the deduction for one hole, but actually two holes for the two angles. So it's 0.5 square inches. Okay. And the required, required AG is equal to 2.303 square inches plus 0.5 square inches equals 2.53 square inches. So the required is 2.53, and then we can choose a member from the menu for double angle. Okay, so we can see that two double angle L 3 by 3 by 1/4 inch would qualify. Cross section is 2.88 square inches, and Rman is 0.926. So it should be okay for that. Okay. So similarly, you can also consider the double angle with the standard thickness of 5/16 inches. So you can practice, repeat the same procedure. You'll find the deduction for the one hole gonna be 0.6025, and the required cross section is 2.65 5, and we can choose a member from the menu, like 2L 2.5 inch by 2 by 5/16, right? So for this member's cross-sectional area is 2.64, and our man is 0.744, right? So they would all qualify. All right. Okay, and then so those members would all those members would work. So we want to select one of them and check the VPN for the selected members. So we select L 3.5 by 3.5 by 3/8 angle, single angle, right? So that's a single angle, and then check if its VPN qualifies. So like we have done before, that's first we want to check yielding, right? Check yielding. So VPN based on yielding equals 0.9 times Fy times Ag. So that is equals to 0.9 times Fy, which is 50 KSI times Ag. Ag from the menu, we find Ag is 2.5 square inches, equals 112.5 kips. All right, and then we want to check fracture. So we want to check fracture. So fracture VPN equals 0.75 times Fu times AE. So we want to calculate U first, right? So AE, and AE equals U times AN, and then U equals 1 minus X bar divided by L, right? So so this is the angle, right? So you want to find out the centroid, the distance from centroid to the interface. So from the menu, we find out X bar is 1 inch. So it's 1 minus 1 inch, and divided by L. So L is the length of the connection, right? So we assume the spacing So this is a truss member. So this is a tension diagonal member of the roof truss. So I suppose it's like an tension member bolted on a gusset plate. Right? So that's the gusset plate. Okay. And how many bolts? So assume that the 3 bolts, we use 3 bolts. Okay. And the spacing of the bolts is 5 inches. So 5 inch. All right. And then the walkable gauge distance given by the code is 2 inches. So the distance from the center of the bolt to the other edge is about 1.5 inches. All right. Okay. And then so the length L is the length of the connection. So based on our design, the length of connection is 10. It's 10 inches. So U is equal to 0.9. Okay. And then we can calculate AE. AE equals UAN. Right, UAN. So U is 0.9. AN is the gross section. Gross section is where is the gross section? Is 2.5. 2.5 square inches minus the whole area. So the whole is 1 inch, right? So the whole diameter is 1 inch, and the thickness we choose is 3/8 inches. Okay. So from there we get the AE of 1.9125 square inches. Okay. And then the VPN based on fracture equals 0.75 times FU, which is 65 KSI times AE, 1.9125 square inches. And we get the VPN of 93.23 kips. So we notice that this one is smaller than VPN based on yielding, right? Smaller than its numbers. Okay, and then next step is check block shear. Right? Next step. Check block shear. Okay. So let's see the possible failure block would be like. So the angle, 3 holes, So the block tail out will be like this, right? So this is the block gonna be tailed out. Say, right? Okay. And then we also determine the dimension, right? So that's 1.5 inch, and the total length is 15 inches, right? So we are the designer, so we can choose whatever we wanted to choose, as long as the VPN would be greater than PU. Okay, so from the code, block shear VPN would be lesser of okay, so I need a bigger spacing. Okay, so based on the code, VPN is lesser of 0.75 times ANT FU plus ANV times 0.6 FU. 0.75 times the first item is same, ANT times FU plus AGV. So gross section always related to yielding, so 0.6 times Fy, right? So so remember that we always need to calculate the 4 different cross-sectional area, right? AGV, ANV, right? And AGT and ANT, right? So always need to calculate these 4 areas in order to find out VPN. So AGV is the shear plane cross-sectional area, which is the horizontal plane. So which is equal to 15 inches, and times the thickness, 3/8 inches, equals 5.625 square inches. And AMV account for the deduction of the whole areas. So along the shear plane, there are 2.5 holes. So it's the gross area, 5.625 square inches minus 2.5 holes, and the whole diameter is whole diameter 1 inch, right? And times the thickness, 3/8 inches. So AMB equals 4.6875 square inches. And gross tension area, which is the vertical cross section, right? So which is equal to 1.5 inches times the thickness, which gives a number of 0.5625 square inches. And ANT account for the deduction of half holes, so that's 0.5625 square inches minus half holes, right? And the 1 inch hole diameter times the thickness gives 0.375 square inches. All right, and then we want to compare. So we want to compare these two items, right? We want to compare these two type items. So A and V times 6FU equals say I pull 0.6 out, so times A and V is 4.6875 square inches. FU is 65 KSI, so which is equal to 0.6 times 281.25, and then AGV times 0.6 FY is 0.6 times AGV is 5.625 square inches, and times 50 KSI, so equals 0.6 times 304.69. So we know that which one controls? AGV. Oh, made a mistake, sorry. So should be opposite. Okay. So AMV times FU equals 304.69, and AGV times FY equals 281.25. So AGV controls. AGV say governs. All right. So from there we can calculate phi PN for the block shear equals 0.75 times ANT times FU, which is 0.375 times FU is 65, and plus 0.6 times 281.25 equals 144.8 kips. Okay, and then we compare the results. Which one controls? It sounds like fracture controls, right? Fracture gives the smallest VPN, right? So fracture controls. So phi PN is based on fracture, which is equals to 93.23 kips, and that is just greater than PU, right? PU is 84 kips. Okay, so we're good, and we're not overly conservative, so we're okay. All right, so So single member works. Single angle L 3.5 by 3.5 by 3/8 works. All right. Thank you for watching.